Let's take for example, an industrial furnace. The inside wall of the furnace is made of a ceramic layer that is 2 cm thick, with a thermal conductivity of 20 watts per meter Kelvin, followed by a brick layer that is 15 cm thick, with a thermal conductivity of 1.31 watts per meter Kelvin, followed by a composite webbing, which provides support for the furnace's insulation. The composite webbing has a 20 cm thickness, a thermal conductivity of 0.5 watts per meter Kelvin, and a wall thickness of 2 cm. The webbing forms square hollow cells that have a 23 cm side length. Each cell is filled with fiberglass that has the same thickness as the webbing for insulation, and a thermal conductivity of 0.04 watts per meter Kelvin. The outside wall of the furnace is made of concrete that is 20 cm thick, and has a thermal conductivity of 1.1 watts per meter Kelvin. An air gap between the composite webbing and concrete on one side and the brick on the other side results in the contact resistance of 3 Kelvin per watt on both sides of the webbing. The temperature of the inner furnace wall is 1500 Kelvin, while the temperature of the outside wall is 350 Kelvin. What is the average rate of heat loss per unit surface area of the furnace's wall? What is the heat flux through the composite part of the wall and through the fiberglass part? Draw the temperature profile across the wall under this condition. If the temperature at which the composite material would be damaged is 1600 Kelvin, then what is the maximum temperature that the inside wall of the furnace can have? Let's start by considering a square element of the wall that has a 0.23 meter side length. The element cuts across all of the wall's layers. For each layer, let's calculate the cross-sectional area that is perpendicular to the direction of heat propagation. The cross-sectional area of the element is equal to 0.23 times 0.23, which is 0.0529 meters squared. This is the cross-sectional area for the ceramic layer, the brick layer, and the concrete layer. The cross-sectional area of the composite part of the wall is equal to 0.023 times 0.02 plus 0.02 times 0.023 minus 0.02, which is equal to 0.0088 meters squared. Finally, the cross-sectional area of the fiberglass part of the wall is equal to the total area of 0.0529 meters squared minus the composite area of 0.0088 meters squared, which is equal to 0.0441 meters squared. Next we are going to calculate the thermal resistances of the different layers of the wall. The contact resistances between the composite layer of the wall and the brick, and between the composite and concrete wall layers, are both given as 3 Kelvin per watt. We then use the thermal resistance formula to calculate the resistances of all of the wall's layers, where the thermal resistance is equal to the thickness of the layer divided by the thermal conductivity of the layer times the surface area of the layer, and so we get the shown values. Note that due to the high thermal conductivity and small thickness of the ceramic layer, its thermal resistance is very small. Furthermore, notice that we use the cross-sectional area of the composite part of the wall when calculating the thermal resistance of the composite layer, and we use the cross-sectional area of the fiberglass part of the wall when calculating the thermal resistance of the fiberglass layer. Since the composite and fiberglass wall layers conduct the heat in parallel, we calculate the value of their combined parallel thermal resistances as being equal to 32.446 Kelvin per watt. The total thermal resistance of the furnace's wall can then be obtained by adding the thermal resistances of all of the wall's layers that are in series. This is equal to the resistance of the ceramic layer, plus the resistance of the brick layer, plus the contact resistance between the brick and composite layers, plus the combined parallel resistance of the composite and fiberglass layer, plus the contact resistance between the concrete and composite layers, plus the resistance of the concrete layer. This gives a total wall thermal resistance value of 44.067 Kelvin per watt. Next we calculate the heat diffusion rate through the wall element as negative. The temperature difference across the entire wall, divided by the total thermal resistance of the wall, that we previously obtained. Notice that when the temperature difference is multiplied by the minus sign, it becomes equal to the inner furnace wall temperature minus the outer furnace wall temperature. After substituting the values of the variables, the heat diffusion rate through one wall element is found to be equal to 26.097 watts. In order to obtain the heat flux, or heat diffusion rate, through a unit area of the wall, we divide the heat diffusion rate by the cross-sectional area of the wall element to get a heat flux value of 493.321 watts per meter squared. The equation for the heat diffusion rate through the composite part of the wall can be rearranged and written in terms of the temperature difference across the composite part of the wall. Similarly, the equation for the heat diffusion rate through the fiberglass part of the wall can also be rearranged and written in terms of the temperature difference across the fiberglass part of the wall. We note that since these two wall resistances are in parallel, the temperature difference across them is the same. We can thus combine these two equations to obtain the shown relationship between the heat diffusion rate through the composite part of the wall and the heat diffusion rate through the fiberglass part of the wall. Another relationship between these two variables can be obtained from the total heat diffusion rate, which is equal to the heat diffusion rate through the composite part of the wall, plus the heat diffusion rate through the fiberglass part of the wall. This equation can be rewritten in terms of Q dot composite, then substituted into the previously obtained relationship between Q dot composite and Q dot fiberglass, to obtain the shown equation. That is a function of Q dot fiberglass only. We then solved for Q dot fiberglass and obtained a value of 7.468 watts. The heat flux through the fiberglass wall layer can then be calculated by dividing Q dot fiberglass by the cross-sectional area of the fiberglass layer to obtain a value of 169.342 watts per meter squared. Next, we substitute the value of Q dot fiberglass into the equation for Q dot composite and find that Q dot composite is equal to 18.629 watts. Finally, we find small q dot composite to be equal to 2116.932 watts per meter squared. Note that due to the smaller thermal resistance of the composite wall layer as compared to the fiberglass wall layer, most of the heat is transferred through the composite layer, despite its small cross-sectional area. The plot of the temperature versus the distance across the furnace's wall can be obtained by calculating the temperature values at the wall's interfaces versus distance, then connecting these values with straight lines. Straight lines can be used to connect these points, because we know from the heat diffusion equation that the relationship between temperature and distance along any homogeneous part of the wall is linear. Now let's calculate the temperature at the interfaces between the layers. First we tabulate the resistance R for each layer. Then we can calculate the change in temperature across each layer as minus Q dot, which is 26.097 watts, times R. So for example, the temperature change across the ceramic layer is minus 0.493 Kelvin, and was obtained by multiplying minus 26.097 by 0.0189. And the temperature change across the brick layer is minus 56.500 Kelvin, and was obtained by multiplying minus 26.097 by 2.165. At point 1, the distance x is equal to 0 meters, and the temperature is equal to the inner furnace temperature of 1500 Kelvin. At point 2, which is the interface between the ceramic and brick layers, x is equal to 0.02 meters, and the temperature is equal to 1500 Kelvin, plus the change in temperature across the ceramic layer of minus 0.493 Kelvin, which is equal to 1499.5 Kelvin. That point 3, which is the interface between the brick and the gap, X is equal to 0.17, and the temperature is equal to 1499.5, plus the change in temperature of minus 56.5 Kelvin across the brick layer, which is equal to 1443.0 Kelvin. We can similarly obtain the temperatures between the remaining wall layers. Finally, we verify that we end up with an outside furnace wall temperature of 350 Kelvin. As we can see from the plot, the curve is almost flat between points 1 and 2. This is because the temperature on the outer side of the ceramic layer is only slightly smaller than the temperature inside the furnace, due to the small thermal resistance value of the ceramic layer. Also notice that, as mentioned before, the contact resistance shows on the temperature versus distance plot has a sharp vertical temperature drop. We are given that the temperature at which the composite layer would be damaged is 1600 Kelvin, and asked to determine the maximum allowable temperature inside the furnace. The maximum temperature in the composite layer occurs on the composite side of the gap between the composite and brick layers, since this is the side of the composite layer that is closest to the inner furnace wall. We hence set this temperature equal to 1600 Kelvin, and solve for the temperature inside the furnace. We divide the furnace's wall into two regions. The first region is comprised of the ceramic layer, the brick layer, and the contact resistance between the brick and composite layers. Adding up the values of the resistance for these three layers, we find that the resistance of this first region is equal to 5.1839 Kelvin per watt. The second region comprises the parallel composite and fiberglass layer, the contact resistance between the composite and the concrete layers, and the concrete layer. Adding up the values of the resistance for these three layers, we find that the resistance of this second region is equal to 38.883 Kelvin per watt. We then write the heat diffusion equation for both regions, noting that since the two regions are in series, heat flows at the same rate through both of them. We rearrange the equation as shown. Then substituting in the values, we have R2, which is 38.883, multiplied by minus delta D1, which is the inner minus 1600, is equal to R1, which is 5.1839, multiplied by minus delta E2, which is 1600 minus 350, or 1250. Finally, we rearrange the equation and calculate the inner furnace temperature to be 1766.65 Kelvin.